Hi and welcome back to My Physics Teacher by Mr. Cannon. Today we're going to focus on equation practice, and today's topic is forces, with a focus on Hooke's law and elastic potential energy. Before you start, make sure you have a calculator with you and give each question a go before you see me going through the answers. Question 1, we've got a spring that has a spring constant of 50 newtons per metre, so we're going to underline that. And we want to calculate the force, box around it, needed to stretch the spring by 0.2 metres. We're now going to write out all the key terms in shorthand. So force F equals F, we're not sure what that is, it's what we're trying to find. K, the spring constant, is 50, and the extension is 0.2. It's best practice to keep the units just in case we need to do a conversion, which we will do later. We now need to choose the right equation that has F, K and E in. So we should recognise that force is the spring constant times extension. We now can substitute the numbers in, so rather than K 50 and rather than E 0.2. Put that into a calculator, 10 newtons. Number 2, we've got the spring constant of 3000 newtons per metre. We want to calculate the force, put a box around it, and the spring is 5 centimetres. Just like we did before, we write it out in shorthand. So F, force is still F, that's what we're trying to find out. K is 3000. And E is 5 centimetres, reminding ourselves we need to divide by 100 to turn it into metres. Next, again, we need to choose an equation that we're going to use. So force equals spring constant times extension. Rather than K, we can write 3000. And as a reminder, our extension is the 0.05 that we've converted into metres from centimetres, 150 newtons. Number 3. Again, we're going to calculate something. This time it's the spring constant. We know it's extended by 4 metres, and the person here is 70 newtons, which of course weight is an example of a force. So although it says weight, we can recognise that as force, 70 newtons. Spring constant is now the unknown, K, and extension 4 metres. Just like the other ones, we can recognise the equation force equals spring constant times extension. Now we're going to substitute in the numbers, so 70 for force, spring constant is now just K, and extension is 4. For both of them, we need to divide by 4 to get that by itself, to make K the subject, so 70 divided by 4 gives you 17.5 newtons per metre. For number 4, we've got the spring constant, this time we're calculating the extension, and now we've got the force of 4 newtons. F equals 4, K is the 2.5, and E is the unknown, so that's going to stay as E. We now again need to choose the right equation that has F, K and E in, so force equals spring constant times extension. Rather than F, we can now replace it with 4. Rather than K, it's 2.5, and E is the unknown. We want to get E as the subject, so we need to divide both sides by 2.5. So now 4 divided by 2.5 will give us the value of E, and using a calculator, that comes out as 1.6 metres. For question 5, we want to calculate this time the potential energy, the elastic potential energy, and we know it's extended by 0.4 metres and the spring constant is 5 newtons per metre. So for elastic energy, you could just put capital E, but I'm putting E and small e for elastic energy. The extension is 0.4 and the spring constant is 5. We now need an equation that has elastic potential energy, extension and spring constant in, and that gives us this one. E is 0.5 times K times E squared. We can now substitute in, so rather than K, we can write 5, and E is 0.4, but we need to remember to square it. So elastic potential energy, 0.5 times 5 is 2.5, and 0.4 squared is 0.16. We can then continue to use our calculator by multiplying those two together, and that gives an answer of 0.4, and the unit is joules for energy. In the next one, we've got a spring constant of 1,400, and we again want to calculate the elastic potential energy if it's extended by 2 metres. So EE, you could just put capital E, that's the unknown. K, our spring constant, is in newtons per metre, 1,400, and the extension, it's got longer by 2 meters. We now need to again choose the right equation to use that has these three in it. And like before, elastic potential energy is a half times spring constant times the extension squared. We can then substitute in the values, so 0.5 rather than k is 1400 and the extension is 2 squared. So that's 0.5 times 1400 is 700, 2 squared is 4, and then we've got the answer of 2800 joules. For number 7, this time we have got, again, to calculate the elastic potential energy, we've got an extension of 25 centimeters. We need to keep that in mind. There's going to be a conversion involved, and the spring constant is 0.4. So we're going to simplify. K is 0.4, and the extension is 25 centimeters. To convert into meters, there's 100 centimeters in 1 meter, so we divide by 100. Again, we're going to need to choose our equation, which, like last time, is elastic potential energy equals 0.5, so a half, times spring constant, times the extension squared. Substitute in the values, 0.5 times 0.4, and then we need to do 0.25 squared. We can then simplify, so half of 0.4 is 0.2, and 0.25 squared is 0.0625. Put that into a calculator, and the elastic potential energy that we're trying is 0.0125 joules. Then on to the last question. We've got the spring constant that we want to calculate this time. It extends by half a meter, and we've got that amount of energy stored, 2500. So elastic potential energy is 2500 joules. The spring constant, we're trying to find it, that's why it's got a box around, and the extension is 0.5 meters. We now need to choose the equation again that has those three terms in, and it's the same equation as it was earlier. So it is E for energy, elastic potential energy is 0.5 times K times E squared. We can now substitute in the numbers. This time, energy is 2500. That equals 0.5. K is the unknown, multiplied by 0.5 squared. Now, I always prefer to simplify before I start to rearrange to find the subject, K. So 2500 stays, 0.5 stays, and then 0.5 squared is 0.25 times K. So now 2500 equals half of that, because 0.5 times 0.25 gives you 0.125. And now we want to get K as the subject, so we need to divide both sides by 0.125. So 2500 divided by 0.125 gives us a final answer for the spring constant, which comes out at 20,000, and then it's newtons per meter. Many thanks for watching, and if you've enjoyed this video, please remember to like, share, and subscribe. See you next time.